Hi, my name is Jonathan Van Schenck, and I'm part of the OPE group here at Oregon State University. And we study the optical and electronic properties of organic semiconductors. And today I'm going to be presenting some of my research on organic single crystals. But why are we interested in studying organic semiconductors specifically? Well, organics are solution processable and tend to be much lower cost than their inorganic analogs like silicon. Additionally, organics can be deposited onto flexible, lightweight substrates and have tunable properties. And all of this makes them a very enticing option for creating electronic devices with. However, being able to create efficient devices requires us to understand well the properties of the materials themselves. So today I'm going to be talking a little bit about the properties of one specific organic semiconductor called anthrodiethiophene. So here you can see an image of anthrodiethiophene as it's dissolved dilutely in solution. It's got kind of this nice orange color to it. And over here you can see the chemical structure of anthrodiethiophene. Now, ADT is really interesting for two reasons. The first is that it has this ring structure that forms the backbone of the molecule, and all of these alternating single and double bonds. Now, those alternating single and double bonds allow electrons to delocalize over the entire length of this molecule, which makes it very optically active. So essentially, photons are able to come in and be absorbed by this molecule and create excited states called excitons that can move across the backbone of ADT. Now, after a while, that excited state, after it's been moving around, is going to collapse and release a photon in an event called photoluminescence. Now, that excited state is going to last for a certain period of time, called its excited state lifetime. And by measuring how long it takes from that absorption event to that fluorescence event can tell us information about the properties of the exciton itself. So that's going to be one key idea that I'm talking about here, is we're going to use the excited state lifetime to measure the properties of the exciton that sits on the backbone of ADT. Now, the other reason why ADT is interesting is because of its molecular side groups. You can see labeled here with these R's. Now, we can interchange these R groups for different molecular structures, like you can see down here at the bottom of the screen. And those different side groups don't really affect the optical properties of ADT when it's isolated in solution. Remember, the exciton likes to sit on the backbone of the molecule. But these different side groups do affect the way that ADT packs in the solid phase. To illustrate this, I've got two microscope images of crystals of anthrodiethiophene with different functionalized side groups. And you can notice that this picture right here is slightly oranger, this picture right here is slightly more red, and that's essentially pointing to the fact that the different side groups are creating slightly different packing structures of the crystal, which have different optical and ostensibly electronic properties as well. Let me illustrate this a little bit further with some schematics here. So here we have a schematic representation of the crystal packing structure of ADT for various different side groups. So for the TSBS side group up here, you can see that the molecules tend to pack in a one-dimensional structure, where the backbone of the molecules tend to stack in this almost stepping stone pattern through 1D. For a different side group, for TES, you can see that instead it forms a two-dimensional brickwork structure. And then for TBDMS down here at the bottom, they also form a one-dimensional stack, but this time the molecular backbones are very well aligned with one another. Now, the reason why this is particularly interesting is different packing structures should have different excitonic properties. For example, excitons that are sitting on the back of one of these molecules right here are able to hop to adjacent sites. And if you're in this one-dimensional versus this two-dimensional structure, by increasing the number of adjacent molecular sites, it's easier for the exciton in this case to move through the crystal than it is in this case. And similarly, because of the really great alignment of the molecular backbones for this side group over here, it's also much easier for the exciton to move through the crystal. So essentially, we expect more mobile excitons as you move down the page. So this is going to be the other key idea that we're going to study right here, is we're going to, by looking at different molecular side groups, create different packing structures. And then we're going to bring in our key idea from before of using the excited state lifetime to study what exactly are the properties of these excitons that we get from different packing structures. So let's look at what the excited state lifetime of some of these molecules looks like. So here is plotted the probability density of the excited state lifetime for TSBS, both in solution and in crystal. So on the horizontal axis is being shown the time delay between when the photon is absorbed and when the photon is emitted, essentially the lifetime of the excited state. And then on the vertical axis is giving the probability that any particular excited state is going to have that specific lifetime. So here in orange in solution, you can see that it's more or less equally probable on this time scale that an excited state is going to decay early or late. And that's because when these molecules are floating around in solution, that you just have this exciton that's sitting on the backbone, and it's going to live for as long as it's going to live. But when you move into the solid state and you begin forming this one-dimensional stack here, things change, where it becomes much more likely for the excited state to decay on a short time scale rather than a long time scale. Now, what's happening is because the exciton is able to move through the crystal, it can hop from one molecule to another. Each one of those hopping events makes it more likely that your excited state is going to decay, and that's what you're seeing in this figure here. Now remember, for different side groups, if you have instead a two-dimensional structure, it's easier for the exciton to move through your crystal, and what we see is that this weighting towards short lifetimes becomes more pronounced. It's even more likely that the excited state is going to decay on a short time scale. And again, when you move to crystals where you have really great alignment of your molecular backbones and the excitons can really easily move through your crystal, this effect becomes even more pronounced. So essentially what we're seeing here is, again, we're kind of taking two key ideas. First, that we can study the lifetime of the excited state to gain information about the exciton that's created. So a photon will come in, it will create this excited state, and then sometime later that photon will be emitted. And by looking at that process, we can get information about the exciton that existed there. And secondly, by changing the side groups that are attached to this ADT backbone, we can create different kinds of packing structures which we expect to have different kinds of excitonic properties. And by bringing these two ideas together, we're able to demonstrate that when you have better molecular alignment or more neighbors, essentially when it's easier for your exciton to move through your crystal, your excited state will have a much shorter lifetime, and then we can measure and quantify that. So by doing this whole process, we're able to gain a much better understanding of the excitonic properties inside of these crystals, and hopefully this will enable us to build better and more efficient electronic devices for the future. Thank you.